So this portion is about topology, mapping, and neighborhood collectives. So the basic idea in topology mapping is the following. So in your program, you have a bunch of processes that communicate with each other, and the nature of that communication, that is, who communicates with whom and how much, is a feature of your application, of the needs of your application. So if you're doing a stencil computation where you need to communicate with your nearest neighbors in each dimension, that's a kind of communication pattern where the communication is kind of localized. It's nearest neighbor. If you're doing something else where you need to do an all-to-all, then your communication goes all over the place. But the idea here is that if you can somehow specify this communication pattern, either to MPI, to the MPI implementation, or to the system at the time the jobs are launched, it may be possible to launch your job, to launch the processes on the machine in such a way that most of the communication is sort of localized, in the sense that most of the communication, say, happens within a node rather than going across the node, which is more expensive. Or if it goes across nodes, it goes to nearby nodes, not some nodes far away where there could be contention and so forth. So the whole idea is, how do you do that? So there are two ways in which that could be done. The first method is, which doesn't tend to work so well in practice, but it is a way nonetheless, is suppose you are able to convey this information to the system, to the job launcher, or wherever you're running, before you run the program itself. Suppose you are able to provide a graph or a file or something that says who's communicating with whom and how much, in some way, assigning weights or something which means where the larger number indicates you're communicating extra. Then the job launcher on that system could read that information and launch your processes such that, where do 0, 1, 2, 3, 4, 5, all these processes go? Typically, without any special information, it would either do it in a round-robin fashion, launch rank 0 on node 0 and then 1 on node 1 and so forth. Or if it's a multi-core system, it will launch the first few ranks on node 0 just to fill up all the cores, then the next few ranks on the others and so forth as it goes. Those are the defaults. It could do something else other than the default if it had your communication information and if it knew what to do with it, because this kind of mapping of this communication pattern onto the hardware is not an easy. It's not an easy problem. It may not have an easy solution. But it turns out that this is not typically supported on batch systems. What is supported is that you can specify, particularly on clusters, you could specify a list of hosts in any order, and then it would launch rank 0 to n-1 on those hosts in that order. So you're effectively doing the mapping by specifying this host name file in the order that you're specifying. And you may not know what order to use there as well. Other options typically are you can control how many processes get launched on a node before it moves on to the next node. So if you want 2 at a time, like 0 and 1 on one node and 2 and 3 on the other, 4 and 5 on the other, those kinds of things. Those are simple mappings, but they don't take into account the knowledge of the communication pattern. The other method, which is for which there are functions in MPI, which are called the MPI process topology functions, which is what I'm going to cover, is the way that works is you launch the process as before. There is no change, but as soon as you launch your program, the first thing you do after that is to define the communication topology, either as a graph topology or a Cartesian communication topology, by calling MPI functions. There is an MPI Cartesian, and we'll see what those functions are to define a Cartesian or a graph. Cartesian is for stencil computation, nearest neighbor. And when you do that, what you're saying effectively is the communication in my program follows this nearest neighbor Cartesian type of communication, or it's more general than that. It's actually a graph where I'm actually specifying where which nodes communicate with which other nodes, and some information about how frequently or how much is the communication. So you can pass this information to these MPI functions, and they can take that and return a new communicator, a different communicator, where the ranks of the original process might be different. That is, what is rank 0, 1, 2, 3 in COM world may have ranks 0, 5, 7, 9 in this new communicator, right? So the processes have not moved. Nothing has changed. They've just got a new rank in another communicator, right? And the way that this mapping has been done is by the MPI implementation in such a way that the communication in this new mapping is more efficient than the communication with the old mapping because of the information that you have provided. And then if for the rest of your program, if you just use this new communicator instead of MPI COM world, and the processes use their ranks in this new communicator and not in COM world, then you're operating in a way that is more communication efficient. Does that clear? I find that the basic idea is it takes a little while for sometimes to grasp, but once you get that, the rest of the which functions to use and how to use them is just detail. Yeah, how does MPI reorder is a good question, because the reordering is often not easy. That is, given this mapping, it might be an NP hard type of problem to find an optimal mapping. But assuming an MPI implementation can do a reasonable job of the reordering, what you're given is a new set of process ranks, and if you communicate using those ranks, then the mapping of those ranks is such that they are located nearby. They are not located all over. And so the communication is more efficient. And one thing that you need to do in this, or you should do, is this should be the very first thing you do in your program before you have generated any data or created any state in your program. Because if you have already done that and then you do this mapping, then you have some data or some state that has been generated using the old ranks in MPI COM world, and now you have new ranks in this new communicator. You'll need to ship this data from the old ranks to the new ranks just to get all the data in the right place. That'll be expensive. So it's not something you do in the middle of your program. It's a good idea to do right in the beginning before you do anything else, and then just instead of COM world, you use the new communicator. So for example, so suppose you had a program where you had 8 processes, and the communication graph was as it is shown here. And what this graph means is that 0 communicates directly with 3, 5, and 6. And these numbers reflect, in some sense, the amount of communication. It could mean the number of messages. It could mean the size, the total amount of communication. Just think of it as the larger means you're doing more communication. So there is a lot of more communication between 0 and 3 than 0 and 6. And there is a lot of communication between 5 and 6, for example. So that's the communication graph in your program. How do you find that? How do you know what that is? So for that, you will need to know somehow. There could be tools available, performance tools and there are tools like that can give you the communication profile of your program, and that you could run once just to know what that is. Now, if these ranks were mapped onto let's say a 4-node system in the default way, and this is 4 nodes with 2 cores on each node, then the default way would be to assign, say, rank 0 and 1 on node 0, 2 and 3 on node 1, and then 4 and 5, and then 6 and 7. So if you did that, then and then you calculated what communication happens, say, across nodes, then this is the sort of communication that happens across nodes. And we are assuming that it's faster to communicate within a node than across nodes. So you want to really arrange the processes in a way that more of their communication is within the nodes than across nodes. So instead of that, if you had launched processes like this, 0 and 3, and then 1 and 2, and then 5 and 6 here, and 4 and 7 here, then there's much less communication happening across nodes. There, some of these nodes don't even communicate with each other. So it's just a different mapping of ranks to processes, but you'll get better performance this way because most of your communication is local. So the idea was, how do you get this kind of mapping in the first place? So I said the first option is you somehow specify that graph to the job launcher and have it figure out, but usually they cannot do that job. Or you somehow manually figure this out, that this is a good mapping, and then you can provide a list. You can say launch 0 here and 1 here and 2 there. It could do that, but it's not easy for you to do that as well. So the other way is the MPI way, is where you start your job in the default way like this, and then you call the MPI graph topology function that specifies a graph topology. We'll see how that is. That aspect of it is just detailed because it's calling a function and passing that graph information to that function, and then MPI does the rest for you. And assume that you have a good MPI implementation that could, given this information, would know how to do the mapping. So the result of that topology constructor function is a new communicator in which 0 is still has rank 0. Rank 1 in COM world has a new rank in this new communicator. It's 3. And similarly, 2 is now 1 in this new communicator, and so forth. So you have a new mapping in a new communicator. Nothing has moved. The processes have not moved anywhere. They are where they were. It's only a new mapping. That's why it's called virtual process topologies. Now, if you did this at the very start of your program, before you generated any data, and from now on just ignored MPI COM world, it'll always be there. You cannot get rid of it, but you don't use it at all. And you only use this new communicator that MPI gave you. It's as good as having a nicely mapped set of processes to hardware in a way that communication is more efficient because it's localized, right? So is this concept clear? Because if that is clear, then the rest I said is just the mechanics of how do you pass the information to MPI. But I found in the past that sometimes this is not clear, and this is where we get stuck. Yeah.
Is there any open source MPI implementation that actually does this?
There's a libtopomap type library called that has done something. I'm not sure what the current state of. So if it's a Cartesian topology, it's easier to do. With the graph topology, I'm not sure what the current state is. But there has been at least research efforts like the libtopomap or something like that is the name that has done a good job of this remapping. But again, it's a chicken and egg problem. Unless you use it and show the implementation that you're not doing anything, they won't do it either. So the pressure has to come from the users as well. Yes?
So if you know the communication pattern in your application beforehand,
yeah,
you should instead of doing the reordering, you should tell the MPI to launch in the way initially instead of doing the reordering.
Yeah, but it might be difficult for you to know. Let's see, this is only 7 processes, and even then it's kind of hard for you to come up with this mapping. Suppose you had 1,000, and some kind of graph in there. It would be hard for you to come up with this exact list of the exact mapping, how to do that, right?
If you can tell the MPI launcher that this graph shouldn't be able to.
Yeah, that's what I'm saying. That's one method, is passing this graph to the job launcher, but it doesn't. That it's not so. That facility doesn't exist typically. Very basic. They can do very basic things. They cannot take this graph and do it. That's usually not available. So I'd say MPI supports two types of process topology: a Cartesian and a graph. Of course, graph is the most general, and that could be used for Cartesian as well, but it's intuitive to think of Cartesian as a 2D or 3D mesh, and who are your neighbors in the left and right. So there is support for that. So not only you can specify this topology, but it gives you a whole bunch of convenience functions, because finally you have to do the communication yourself, and MPI sends and receives need to know the rank of the destination and the rank of the source. So when you're communicating with your neighbors in a 2D or 3D Cartesian topology, you need to know what's the rank of the process above you or below you or left or right, and in the third dimension. How do you can again calculate that based on the sizes of the thing, but that's error prone. There are convenience functions in MPI to just query who is my neighbor up, down, left, right, and other such features. So all that is provided. And there is a third feature that we'll cover is there are new collective functions defined in MPI 3 that do communication in what is known as a neighborhood, and the neighborhood is defined by these graph and Cartesian topologies. That is, whoever you are directly connected to are your neighbors, and you can do an all gather or all what's it? I think it's an all to all and all gather, but that happens only within the neighborhood, only the ones you're directly connected to, not everybody. So if you're doing a stencil computation, you could define the neighborhood. You can define the Cartesian topology, and instead of doing sends and receives, you can do an all gather or all to all v. That will happen only among the nearby. So it's potentially more efficient to do the communication that way. So let's look at how do you specify a Cartesian topology. Cartesian is a regular 2D or 3D grid. So this is easy. You pass the old communicator, which could be MPI COM world. You pass the number of dimensions in this process grid, 2D or 3D or any number. There is no restriction. Then now you pass. This is the number of dimensions, and this is the size of the dimensions. So is it x times y, or x times y times z, whatever it is. The next parameter is whether the boundaries are periodic or not. So what that means is, suppose you are at the top row of this 2D mesh, and you say, who is my neighbor above? Do you want MPI to return the neighbor all the way at the bottom? Or do you want MPI to say you don't have a neighbor, so it will return MPI proc null? So and similarly on the east and west sides, is your neighbor, if you're on the rightmost edge, when there's nobody to the right of you, do you want the wraparound to happen, that your neighbor becomes the very first? That's your choice. So you can pass the periods as 1 or 0. 1 means periodic, 0 means no. The reorder, the reorder parameter says, do you want MPI to try to reorder the ranks to do a better mapping, and so that's your choice. So, typically you'd want to say yes to get the benefit of this. If you say no, that is 0, then there is no reordering, but you still get the convenience functions. That is, you can calculate who your neighbors are at least easily with the MPI functions that I'll tell you about. But typically you want to say reorder is 1, and what you get is a new communicator on which this topology is defined internally. It's hidden inside the communicator. And if you have said reorder, then potentially the ranks may be reordered, and you'll have to query. You'll need to call MPI COM rank again on the new communicator to know what the rank is for each each process has to find its rank in that new communicator, right? And if you have calculated any data already in your program, you might need to move it around. So that remapping you have to do if you have asked for reordering, that is. If there was no reordering, then you don't need to remap the data because rank 0 remains as rank 0. Is that clear? Any? Okay. So this is just an example of how do you fill those. So let's say you have a 3D process. You have 125 processes arranged as a 3D mesh of 5 by 5 by 5. So this is how you would do it. You would pass the DIMS. You'd create an array DIMS of size 3 and fill it with 5, 5, 5. You want it to be periodic, so you put 1, 1, 1 here, and then you pass these parameters. Here, just as an example, we pass 0 as reorder. You could pass it 1 typically. Now the question is, when you start MPI, you just provide the number of processes. Let's say you say 1024. How do you know what is a good decomposition of 1024? Should it be 512 times 2 or 256 times 4 or 128 times 8 or what else? So the good answer is you want it to be as square as possible. So you don't want it to be lopsided. It's not 512 times 2 usually. You want it to be as square as possible. How do you get that number? So these are the convenience functions I was talking about. There are about 3, 4 of them. The first one will suggest a good decomposition. So what it says is you input the number of processes. As I said, suppose it's 1024, and let's say you want a 2D decomposition. You pass 2 as the parameter, and this output array is a 2D array which will tell you what is a good decomposition for that. Is it 64 times 16 or 32 times 32 or whatever it is? It might suggest 32 times 32. So you don't have to do that calculation, which is easy in 1024 case, but if it was 10,400, then you would not know what's a good one. So you could get that. You can ignore, you don't have to use this value. You can use your own value in any case. This is just a suggestion. So this is just an example which shows how to use that with this DIMS create function. So what you do is you call MPI com size on MPI com world and get the number of processes. Then you call MPI DIMS create with the number of processes, and let's say you want a 3D decomposition. You pass 3, and you pass DIMS, an array of 3, and MPI will fill this array with a suitable 3D decomposition based on whatever is this value p, and you can directly pass that to MPI cart create. So it's a convenience function, as I said. Then of course there are some query functions provided. That is, given a communicator that has a Cartesian topology associated with it, what are the number of dimensions? What are the sizes of the dimensions? And then these two functions are useful. You translate the coordinates of a process to its actual rank. So and vice versa. Translate the rank of a process to its coordinates. So you might want to know, for a process in this 2 or 3D process topology, what is the process's coordinates in that? Is it 5, 5 or 4, 4 or 0, 0, or if it's the topmost element? Because that's needed in your calculation somewhere about the size of the local array you're operating on, or so forth. And similarly, you might need the reverse mapping. Given the coordinates, what is the rank? So those features are available. Then the other thing, as I said, you need to know who your neighbors are in all dimensions, because you need that rank explicitly in your communication. So this function MPI cart shift gives you that. It says you give it the Cartesian communicator, you give it the direction in which you want to know. So this is either 0, 1, whether you want it in the horizontal or vertical or in the third dimension. You give it the displacement, that is I guess it is this thing can be plus or minus, and it can be more than one. So you can ask for not only the nearest neighbor, you can ask for who is the neighbor at a distance of 2 or 3 or whatever. So that level of convenience is also there. And this is the rank of the source, and it tells the rank of the target. So you can not only find your own neighbors, you can find somebody else's neighbors also, because the source is also a parameter to the function. So you could, if you want to know somebody else's set of neighbors, you can pass that person's, that process's rank as the source rank, and then you can find the target. So this is another convenience. You can calculate all this yourself manually, given the sizes of the topology, but it gets error prone when you go beyond 2D. Okay, so that was Cartesian topologies. Is that clear that that should be relatively intuitive, because 2D, 3D meshes are something you deal with for stencil computation. The more general case is a graph topology, which doesn't map to a nice 2D or 3D case. The communication is more irregular. So you can define a graph where the edges represent communication among processes, and you can have define weights on the edges to indicate the amount of communication. So one function for this is MPI graph create, which was defined back in MPI 1 itself. That function has a problem, and so now we discourage its use. There are better functions defined in MPI 3. Yes, it's in MPI 3 that you can use instead. The problem is that this function, as it is defined, it requires every process to pass the entire communication graph of all processes, the whole job at every process. So suppose you are running on running on a big system with 1 million cores, with 1 million MPI ranks, and this communication graph had 1 million nodes and edges, and you'd have to pass that whole graph at every rank, which consumes memory. So the problem is the memory consumption of that. There's no need for that. So this is discouraged. The use of that is discouraged. MPI 3 has defined more scalable ways of passing that graph, where you don't pass the whole graph. You can pass it in a more distributed way. So let's look at it. There are 2 ways in which you can pass it in MPI. One is known as it is the adjacent graph. That is, each process just specifies its adjacency information in this communication graph, whom it is communicating with, whom it's sending to and whom it's receiving from, and optionally the weights information. That is, you can specify the amount of communication. So in this case, the information gets duplicated because each process the sender informs about the destination, and the destination also informs about the sender. So there is that level of duplication. But it's not difficult to specify this. So this is just an example of how you would. I won't go into the details because you can look it up. There are a whole bunch of parameters which you need to specify. How many? Yeah, go ahead.
What happens if the weights don't match?
It should be specified in the function, because MPI is typically careful. It could be an error. It could be ignored or something. It probably is an error, but I'm not sure.
If I use this approach, so the code is not portable, right?
No, the code is portable because your communication pattern doesn't change, right? Whether you run it on one system or the other. It's a communication among MPI ranks. What did you mean by code is not portable?
Like the physical hardware is how the accelerator is.
Yeah, so the mapping of this graph onto the hardware, that is in a system-specific way, but that's done by the local MPI implementation. But let's say you're running your program on 1,000 ranks and a particular size problem, that communication pattern among the 1,000 ranks will be the same whether you're running it on Mira or on the Cray. Now, how those ranks should be mapped onto the Mira hardware or the Cray hardware, that is the difference, and that MPI should do that for you, right? Yeah. So I won't go through the mechanics of filling out all these because you can look at it. And this example also tells you, suppose this was the communication graph, how would you fill out all the parameters on the previous page? So that was one way of doing it with the adjacency information. A second way, an alternate way of doing it is using MPI disk graph create. This is a very general way where you are not restricted to adjacency. Any process can specify any part of the graph so long as they collectively specify the entire graph. Okay, so what that means is rank 0 can specify the connectivity information of some other set of processes, and similarly some other set of processes could specify rank 0's connectivity. That's also allowed as long as together the whole graph is specified. It's just allowed that way. So of course the MPI implementation, when you call this function, the MPI implementation will have to do some communication internally to figure out what the whole graph is, because the whole graph is not specified in any single way. It's in a distributed, very, very general way. So again, I won't go through all these function parameters because it's just tedious. You can look at this later. That suppose you had this kind of a graph, how would you fill in the parameters to call that function? So once you have called that function, as usual, it returns the output of both this graph function and the previous adjacency one is the new communicator that has the graph topology associated with it. And if you had said reorder equal to 1, the implementation might reorder the ranks if it knows what to do, if it has a good, if it thinks it can do a useful mapping, and then you get the new ranks in this communicator that you can use from. Then again, there are some query functions. So you can get the number of, you can find how many neighbors you have. You can find the whole list of neighbors. So it's similar to the Cartesian, where you can find out who your neighbors are and so forth. Those things are available. And of course, since all this feature exists, if you are a library, you might want to know, given a communicator, is there a topology associated with it already? Has the user set a topology or not? So you can query that using this MPI topo test function. So you give an input communicator, and the output is either it's a graph topology or a Cartesian or the new distributed graph topology, the MPI 3 one, or there is no topology defined on the communicator. So if you just passed MPI com world to this, the answer would be MPI undefined. There is no topology.